Good afternoon, and thanks to the organizers to give me this chance to talk here. I'm talking about recent work that I've done, and maybe it's cosmology later. And I skipped the introduction for modified gravity because I assume here everyone knows about modified gravity. And the laser, okay. It's what we have as a standard model of cosmology. We have GR, lambda, and CDM. We usually say it's lambda CDM, but I split GR because sometimes in these days when we do modified gravity, we go for modification of gravity without addressing the late time acceleration sometimes. So what we usually do with any models in physics, we go for observations and theoretical questions and then see if what we can say. And the same is true for a standard model of cosmology. Actually, there are questions about lambda CDM. One is this H-naught tension, which is a few sigmas ambiguity between the prediction of lambda CDM and observations, which it happens at the level of background. There is this sigma 8 tension, which is at the level of linear perturbation theory, and void phenomena, missing satellite problem, maybe in nonlinear regime. And I'm not sure. They can be systematics. So, but in this talk, I am going to talk about this H-naught tension and sigma 8. And there are more questions when we work with Einstein-Hilbert gravity. The one which is actually the main result, the main reason that we usually do modified gravity, as Paulo said, is this cosmological constant problem. And for me, there is one more question that is why GR is unique. So, and I try to answer this question now. And this is a quote by Einstein that what really interests me is whether God had any choice in the creation of the world or not. And then for that, we need a story, which is like this, that God wanted to run a simulation for the universe, and he or she asked for some theories, and then people brought theories. And we have a clue. We have a bunch of theories, and then let's say if they are theoretically consistent. I know maybe some of them are not UV completed, so but if you assume that we have more than one model which is theoretically consistent, then you can in principle ask that why we should work with GR at the level of theory, at the level of observation, because it works. So my idea to answer to this question is just taking average, and it's this. If you ask this question, I don't read it again, but if you ask this question, and then you have two solutions. You say no, and then if you say no, you should just say why GR is unique, and if you say yes, then you should give a way to take care of all the other models. And there is, you can say usually you can say it's not a well-defined question, and it can be true, to be honest. It's not a good. My answer is, as I said, that you should take average. And then if you take average over all the models, at the end, you are working with one model, in principle. So, and then I need to show you that this model, that the average model is unique or not. And I will let you know in a few slides later. This is based on this work. And then the same idea, I guess, in the particle physics, has been done by Erkan Ahmed et al. What they do, they say, let's assume that we have a standard model of particle physics, which are labeled different standard model of particle physics, which are labeled by Higgs mass. And then there's a Reheaton field that can decay to these different models, and they want to solve hierarchy problem in particle physics, actually. But the idea is more or less the same. But OK, the details are totally different. So it's the idea. I start with a model space, which I assume that it has all the theoretically consistent models in it. And then I take average. This one is a symbolic relation. That by average, I mean a weighted average. So I associate a probability to each model. And for my case, it's a kind of e to the minus action, which is inspired by path integral and thermodynamics. Okay, so to do some calculation, I assume I can, for any model, there is a Lagrangian. It's an assumption. And then, as I said, this probability is e to the minus beta Lagrangian. Here I should emphasize that I picked this probability by hand, actually. There are some, I mean, it's inspired by path integral, but it's not exactly e to the minus beta s. But you could go for different types of probability. So I have this, let's say I have n Lagrangian, then I have this Lagrangian, then times to this probability. And this one is normalization factor to make the sum of these weights equal to 1. As an example, I started with higher order gravity. And in 4 dimensions, we know that we have just Ricci scalar and Gauss-Bonnet. The other Lovelock terms are identically 0. If you do that, you get something like this, a Lagrangian like this. But then it's interesting, this Lagrangian is not trivial because it's in family of F, R, and G's. And then this family, we know that not having Gauss gives us this relation. And this action non-trivially satisfies this condition. By non-trivially, I mean if you go to literature, usually people work with R plus f of g, for example. So because there is no multiplication of R and G, so you can satisfy this easily. But then here you could ask something, that if the model space is R and G, and this average is a consistent model, then it should be in the model space itself. So, yeah. Yes, yeah. Yes, if you change that, maybe you don't satisfy this, yeah. But I mean, for me, it was vice versa. I picked that, and then I said, I saw that it can satisfy that. Okay. Then I go for a more general scenario. If the model space is all the analytical function of f of r's, and then I pick a basis for that, r to the n. I will come back to this basis, r to the n. Then I get this Lagrangian, where, sorry, that is r bar as defined as r over r naught, and r naught is a dimensionful quantity. So now I have this beta, one free parameter, which is dimensionless, and then I have this r naught. And in principle, I should do this summation till infinity. And this is the result. It's the f of r model. And then in beta is 1 here, but it doesn't matter. This blue solid line is that Lagrangian. And this yellow dashed line is pure GR, is R, Ricci scalar. And you can see some features here. First of all, it's actually an IR modification. It's not like effective theory that usually gives UV modifications. Okay, so everything happens for small curvatures. Properties, which I say they are universal, and come back to it in a few seconds. One, for high curvature regime, we always get GR back. Then here, in an intermediate regime of curvature, we have a stronger gravity. For curvatures less than R0, we get vanishing Lagrangian, and there is always this sharp transition here. And by universal properties, I mean these properties don't depend on the beta, on the value of beta, and don't depend on the choice of the basis. What do I mean? I mean, because I started with this basis as my Lagrangians, but you could go for something like this, no? Because they are consistent in principle. They are f of r models. So these properties don't depend on the choice of basis. The only thing that depends is the behavior of the model in this intermediate region. It's always up compared to R, but it can be upper or lower. But otherwise, this part is always, I mean, for this one, which you always get a Ricci scalar, and for this part, it's mathematics. It's, I mean, I can tell you with mathematics. If R goes to infinity, the dominant term here is R. So you always get R back. And if R bar, which is here, is less than 1, you can see, because this sum goes to infinity, the numerator goes to 0 compared to denominator, denominators. Oops, okay. So it's it. Just one more comment about the theory side. This Lagrangian here, exactly if you plot it, is exactly like this, okay? And then let me just focus on this R to the n part. It's a f of r model, and then equation of motion. Trace of equation of motion is like this. Let's go for a solution which R is constant, and you get this back, no? This term, T is trace of energy momentum tensor, and this trace of this part. So it's exactly here. Then for n goes to infinity, the right-hand side goes to 1. And this limit doesn't depend on the value of t. So you always get R equals R0 when n goes to infinity. Okay. But I should say, you can imagine what I wanted to say. I wanted to say that this model is not sensitive to the value of vacuum energy density. But OK, mathematically, yes, but then physically, no, because in physics, I have more matter fields here in principle. It's not just vacuum energy density. So I have other matters here. But maybe it's the clue that it's a way that we can think about the cosmological constant problem. OK, just one more. Here, that the gravity depends on the scale. Here, curvature scale we know that it's a screening, actually. Or somehow degravitation. In degravitation, actually, it depends. The scale there is a wavelength. But here is curvature, OK? So you can think that this model belongs to a screening mechanism models. So, OK, let me just forget about this. Now I want to focus on its cosmology. But to do that, first, I do some kind of simplification, okay? Because you can imagine it's very hard to work with infinite terms in the Lagrangian. But yes. And this part has been done with my collaborator, Shant, who is in Shaif University in Tehran. This plot is trace of equation of motion for this f of r, the ubergravity, okay? This plot. And this one is minus Ricci scalar, which is a trace of Einstein tensor. Here, and this axis is trace of energy momentum tensor. So this one is the energy density of the matter field. If energy density of a matter field is high enough, you are in a region that that seems that ubergravity and the general relativity are same. But then if rho is decreasing, then there is a critical density that below that, there is difference between our model and gravity and standard Einstein-Hilbert. And you can see here is a kind of wall. And then for any kind of energy density, we touch this solution. So it says gravity, here it means Ricci scalaries are not, and gravity sector is not sensitive to the value of energy density anymore. So based on this observation, it's very simple, but okay. We go for this simplistic version of the model that there is a critical density. Above that, we have GR and CDM. And below that, we have just dou theta. Okay? So we name it either lambda or CDM, because we don't have lambda for this sector. Just one slide on H0 tension. Actually, it is the measurement of Hubble parameter by high redshift data, which is CMB, is these red lines. And then by local measurements, supernovae are these blue lines. And you can see during the time, it seems there is a tension between these two measurements. It's 2, 3 sigma, but it's there. And this paper from last year, Rees et al., they tried to think about all the kind of systematics, but they couldn't remove that tension. So let's say if this H0 tension is physics, so can ubergravity say something about H0 tension or not? This one is our Friedman equation. For Z below a Z transition, we have this H square is constant, and then above that it's very, the first course in cosmology. It's because we have just called dark matter, it's going to like a to the minus 3. And then, so we have this free parameter here, 1, omega matter 2, and then Z transition 3. We have three parameters. This one is co-moving distance, and for redshifts higher than redshift transition. And if we set this H0, 73, reported by Rees et al. Okay. So we go for the best fit of these two remaining parameters, Z plus and omega matter plus. And it's our best fit somehow. Z transition is here, and then omega matter is here. And you can see the red and blue are for BAO and CMB peak, first peak, which is the distance of the CMB towards us, which is a background quantity. And then this black and yellow is additional supernovae. And we think that we can understand that why it's very narrow. I guess it's like a standard cosmology, because we are working with a spatially flat scenario. And this is the plot of chi co-moving distance. You can see there are few other points here. For example, this BAO, high redshift BAOs from Lyman alpha. It seems there is a tension between these two data points and the lambda CDM. We came a little bit down, but we cannot touch them, so it's still there. But I have to say, they are actually very preliminary results, because we need to take care of, because we have one additional degree of freedom in principle. So when we calculate chi-square, we should take care of that, and we don't do perturbation theory, which is very restrictive actually. Okay, it's up to here. But in principle, I guess the key for me, a message for me is this ubergravity can show us a kind of framework that maybe gravity should change. The gravity itself should change depending on the redshift. I mean, it's not like adding a cosmological constant or dynamical dynamical dark energy. It's just a switch between two kinds of physics. Okay. And then perturbation theory, one slide on sigma 8. You can see that here, these black circles are Planck, and these ones are low redshift measurements. Sigma 8 is a little bit less with local measurements. And this DES, I guess 1 or 2 months ago, report by DES, they say the tension is less, but it seems there is still a kind of tension there. Okay, so it's not bad if we look at the linear perturbation.
Actually, that is a 28 parameter space, so the gas data are not in touch. That is just a two-dimensional projection. So when you look at the 28-dimensional parameter space, there is no touch.
Okay, yes. So it seems there is no tension in sigma 8, but I don't know. I mean, because I read the abstract, I'm not expert in the details. They say it's less than previous, and depending on what do you say to tension, because I mean, if you say 2 sigma is not a tension, I agree, actually. But yes, I agree. I mean, let's put it in this way. I'm trying now to say that how linear perturbation works in ubergravity, and I have something for that. I mean, I want to see if I can just take care of this 1.5 sigma or not. If we want to do that, it's the total density, and I should compare this total density with this critical density in principle. And then here it's interesting because these perturbations depends on k. So it means the total density touch critical density, different modes touch critical density at different redshifts. So it's a plot for power spectrum. These blues are at redshift 2, blacks are redshift 0, and reds redshift 1. Solid lines, lambda CDM, dashed line, ubergravity. And you can see that we are at deep dark matter era, redshift 2, as it should be. I mean, we are compatible with exactly, we predict the prediction of lambda CDM. Okay? But then when you come to low redshifts, you can see the difference between our model and their models. I mean, the lambda CDM model. Let me give you 2 scales. This scale is a nonlinear scale, so we don't trust to this part. And this one is sigma 8 scale. And you can see here at redshift 0 that we predict less power. It's good in the good direction, but we should be careful because our model, as you see, is scale dependent. So we cannot just trust to the analysis of the people did for lambda CDM, because for them, as you can see, these solid lines are exactly same, just multiplied by a constant amplitude, no? But our model is totally different for different Ks. So in principle, what people do, as I know, as far as I know, that they just stack all the information from redshift, let's say 0.3 to redshift 0, and then they say there is a tension. But here we cannot do that. If we want to do the same, if we want to say something about sigma 8, we should redo all the analysis with our own model, because we have this K dependency. And it is it. So the main result here is that we predict a scale-dependent power spectrum. And yes, I stop here. OK, for conclusion. I didn't say anything about, we don't know if the sigma 8, I mean, if it's not a tension, so we don't need to solve that. But if it is a tension, we don't know that we can solve that or not. But we have some hints for H0. And for myself, I mean, I didn't say anything about nonlinear parts. But for me, there is one question, remaining question in the theory part, which is that how I can find a way that I can associate the probabilities without tuning. I mean, because I picked these probabilities for models by hand. So I want to know how I can do it in a more fundamental way. Thank you.
Just, I'm curious. I mean, can you do the same analysis in a black hole environment? I mean, so instead of relative to have the distance, and to see these effects?
It should be possible, but I don't know. I mean, we haven't done. But there is something that it depends how. It depends how do you define the density. Because for a black hole, inside the black hole, for sure we are in this region. For outside the black hole, if you want to say, for outside the black hole is if it's a vacuum solution. So we are here in principle. So we have this solution, and you should just connect it to the inside the black hole solution. Yeah.
So how are you deciding what you're allowing yourself to put into the into what you call in your action? I mean, you have GR, which is just only the tensor degree of freedom.
Mm-hmm.
I mean, you're adding things that essentially contain a scalar. Now,
Yes.
I presume that if I redefine the basis that you're in, I mean, took out the scalar explicitly, then you would get your action would be an infinite set of terms that would be highly nonlinear in the scalar field. So I should really add that in, and then why not more? Why not more degrees of freedom? I mean, where are you cutting it off, and so and on what basis?
Yes, I mean, there is no reason to stop, actually, but it's what I could do. I mean, I understand. I mean, I could add massive gravity. I could add vector degrees of freedom. You're right. And as you say, I mean, they are all scalar tensor theory, so I could go for, I mean, in principle, I can go from this Lagrangian to Einstein frame and see what I get there. But in principle, I could start from all the scalar tensor theories, and then, as you say, there is this different types of, kinetic terms, different types of potential, and then I had to take average over all of them. In principle, yes, I had to do that.
Sorry, I mean, if you, for example, want to say, you're picking into consistent theories somehow.
Yes.
So let's say, Hordensky is a consistent theory. Then just a mathematical question. So, you will consider each term, like for example, in Galileo, each term as a separate Lagrangian, or you can put the whole thing as one model. Is it like the same thing? It will be the same?
I guess for me, it means that it's a matter of choosing the basis.
In this case, you said it's the same.
Yeah.
But in that case, which is more complicated, with derivatives and all that, you will not get the same answer. The bases are important, not.
No, if you go for, let's say, for 5 Hordensky Lagrangian, so the bases are 5. But what I am not sure is you have this freedom in the functions.
Yeah.
So should I say different functions are different coefficients or not?
Yeah.
Okay. Thank you.